All right, I think we're live again. Third time's the charm here. Let's see how this all works out. Just going to do a quick audio check at this end. Trying to listen for feedback from a second computer, and we'll see what we can hear. Are you kidding me? Nope. At least not for this one. Let me try one more time. I'm not hearing audio, even though it showed up on the preview. For the sake of Pete. All right. Gonna give this one last try. Reloading the page. Let's try this. Ah, I do have audio again. All right. I'm going to mute that temporarily. And do one last audio check again. All right, I think we are back in business. Of course, I think I've lost all of you now. So I am going to pause for a moment or two. And I'll just put a quick comment on the other feed. All right, I think we're back. We can hear. Fantastic. Okay. My apologies. Again, this did all work in rehearsal, and then of course, one thing goes off the rails, and then we get back. All right. So Kyle, you had a question from earlier. I'm going to bring that up, and then we're going to dive into that one. Find that. I just have to scroll down through the earlier session. Screenshot question. There we go. All right, I'm just opening up the question here. Large area that can describe an equilateral triangle size of like 2. Perfect. Another optimization problem. All right, let me know if, perfect. Just saw you posted there again. All right. So let's take a quick look. So this is number 26, I believe, sorry, 26 from unit 7. And the scenario is that you can look at an equilateral triangle with every side being 2. And what we're going to do is just cut it down the middle, since there seems to be no particular right or left preference. And when we do that, we're then going to inscribe a rectangle inside of it. So like that, or maybe wider and shorter, or as we probably expect, there's going to be some sweet spot where we get a larger area in this scenario. So I'm just going to go back to the other feed so I can see the comments again. All right. There we go. Okay. So please do interrupt if there's anything that specifically you want to look at in this. Here we go. But in terms of the process for solving it just as is, this question essentially boils down to finding the area of the rectangle. And again, don't get deceived. There's areas of the triangle here as well, but that's not something of interest to us. It's simply the area of the rectangle that matters. And then you actually have a choice, and there's no right or wrong answer to this. It really depends on what you think when you first get into this. Certainly, the height of the rectangle is going to matter. The choice is whether you just talk about the width or whether you sort of latch on to cutting it in half in the first place and you sort of call this part here, some people might call that X. Some other people might have called that Y instead of height as well. Is there a preference that you would have looking at this? I'm just trying to bring up the comments again here. And of course, loading slowly. There we go. Is there a way that you thought about this, Kyle? Okay. Then the key thing is just to recognize height and width. So if you're thinking rectangles and you go height and width, then I would look at height and width on the diagram. This whole thing here, get rid of our little X bits here. The width is this whole entire width. Okay. In terms of solving process outside of this, the question asks for maximum area, so you have to have a formula for the area. Otherwise, you can't do anything. So height times width. Once we have that, then you look at your diagram and say, okay, how can I find that? Well, the height, let's say it is what it is, but once I pick a height, I can't choose my width any way I want. I have to choose it so it fits inside this little triangle. And that leads us to sort of a diagram like this, where whatever we pick for our height is related to this part here, but that's not our width. Actually, this is half of our width over 2. And looking at that diagram, the other ingredients that we might reasonably look at are similar triangles. I'm seeing a big triangle all the way on the outside. And I'm also seeing a smaller triangle hiding inside it that has the same angles built into it. Pardon me for 1 second. I'm just going to move the comments on a different screen closer to where I can actually view them. And that didn't work either. Fantastic. There we go. 1 sec. Okay. So this question is definitely putting ingredients together. All right, I need height times width. Where do I see those in the picture? I see them in this kind of diagram with a triangle. What kind of tools do we have for triangles? We've got similar triangles, we've got Pythagoras, we've got trig functions, but when you have one triangle inside the other, the main thing that occurs to me here is similar triangles because of that inside-outside structure. So if we draw the two triangles that we're talking about, try to draw them the same. The outside triangle has a total width of 2, so the base here is 1. The outside was 2 as well. It was an equilateral triangle. And then we have to do a little bit of math here, but we could figure out that 1 squared, let's call this, we already used h and y, let's call it z. 1 squared plus z squared equals 2 squared. Z squared is going to be 4 minus 1, which is 3. So z is root 3. That equals root 3. So we have that kind of triangle. Once we've got that structure, then we look at the small triangle and try to look at the ingredients there. It has a base 2. I'm just going to draw it down here this time. Width over 2. And we know something about the height. This is another common theme. The height of this triangle, this little triangle at the top, is related to the height of my rectangle, but it's a what's left over type of scenario. This height plus the leftovers here, I'm going to call this y, we haven't used anything else for that, plus y is going to equal those two things together. Oh, they equal root 3. So your height is equal to, actually our y value here is what we care about, is going to be root 3 minus h. This little part here is the whole length, root 3 minus the height of the rectangle. The taller I make the rectangle, the smaller my y is. And so we get root 3 minus h. All right. Again, type in if there's any steps in here that are making 0 sense, or if you're looking for hooks for how they would occur to you. Then we go to the similar triangle ratios. So what we want to relate is this h and this w, so that we can get rid of one of them on this scenario. And when we do that, we can use the 1 to root 3. 1 over root 3 is the same as width over 2 to root 3 minus h. Excuse me. That gives us an equation. We can solve it any way we like. I would be tempted to just get everything up onto the main line. So we'd have, let's bring it over to here. Root 3 minus h is the same as root 3 times w over 2. And it's probably easiest actually to solve for w here. We can divide through by root 3, and we can multiply across by 2, and that gives us an expression for the width. All right. And that is something that we can then sub into the area calculation, the area formula. The idea being, I can't set h and w separately because they're locked together somehow by being inside this triangle. But now if you tell me what h is, I'll know immediately what width I can use with that. And then our function becomes just a function of the height. Our area can be determined uniquely by knowing how tall a rectangle I've built. And if that's the case, then we can write our area out as height times root 3 minus h over root 3 times 2. I believe that was all the ingredients. Just double checking. Yeah. All right. Just going to double check because I haven't seen any comments in a second or two. So make sure I'm not missing anything here. No. All right. All right. Once you get to this stage, then we want to maximize. Oh my goodness, sorry. I have a cable that just slid off the desk, and it was what crashed things last time. Give me 1 second. All right, hopefully that'll fix things there. All right, we want to maximize A, and to do that, we're going to look for critical points of A, and that means we're going to find dA, dH, and again, totally up to you how you want to do this. I would probably rewrite the actual expression pull out any constants in the first place and then multiply the h in. We have root 3h minus h squared. Then when we differentiate this, with respect to h, we're going to get the 2 over root 3. We're going to get the root 3 minus 2h, like so. Then once we do that, we are going to set that equal to 0, because that's how we identify critical points. And it actually turns out to be not too bad. We get root 3 is equal to 2h. We can divide through by those terms. And h equals root 3 over 2. And so our w was 2 over root 3. Sorry, it's coming from the last page. 2 over root 3 minus h. Root 3 minus h. Except now we know what h is. And you can do this with calculator work if you prefer, or you can multiply through. That's going to give you 2 over root 3, surprisingly, times root 3 over 2, which actually equals 1. So by the time we're done all this, the optimal dimensions are width equals 1 and height is equal to root 3 over 2. And if you're drawing the actual scenario out here, let's do this and this, it would be 1 across the entire top here. So it'd actually be 0.5 and 0.5 if you were doing the sub-elements. So that's that particular scenario there. Again, I haven't seen any new comments in a bit, so I'm just going to refresh and make sure I'm not missing anything. It seems, no, here we go. We're reloading. There we go. Okay. There we go. For Math House, no. Cobwebbing was covered in the on-campus section, section 02 and 003. The online class does not have, is not responsible for that. If you look at the online course's old exams, you won't find any reference to cobwebbing. Chat. Weird. Okay. Sorry, I'm just getting overloaded by all the Facebook notifications and other stimulus going on right now. And it's hard to tell which ones are actually related to the feed. And how I can get rid of them sometimes. That didn't work. All right. All right. So far, I know I answered Macken's question earlier, though, without any audio whatsoever. So that may or may not have been particularly helpful. Macken, if you're still here and want to follow up on that, I'd be happy to go back. I can bring up the question there. If there are any other questions at all, then basically, yeah, just feel free to type something to the comment window. Sure. So I'm assuming the integral of that arcsine function. So that particular question is just thinking it through, yes. So that would be an excellent building up the muscles for integrals, but it's in some sense not representative of the test question. As we'll see, it requires sort of 3 stages of integration. And typically on tests, we try to cut it down to about 2 at the end of the day, just to make it more manageable. On the flip side, when I say it's a good example for sort of building your muscles for this kind of thing, the idea is that the kinds of approach that you have to use are really are about as obvious as they get. I won't say really obvious because that comes with practice, but they're very clear if you've been doing these for a while. In particular, this question telegraphs a substitution right out of the gate. Ignore the arc sign, looking at the x squared on the inside, the x on the outside, which is its derivative. We would definitely start by doing a substitution to see if that'll simplify the integral. And the substitution that makes sense is the inside function, the x squared, and hopefully that'll cancel out the x by the time we're done. And if we do that, we'll see that is in fact exactly what happens. We bring our dx up or 2x down. We get 1 over 2x dw is equal to dx. And the key thing here is that's how we're going to replace the dx in our integral. For the purposes of this, I'm just going to leave off the 0 and the 1. The hard part here is certainly the actual integration stage. It is integration by parts in a second. Sorry, we're going to get to the integration by parts in a second. I would do a substitution first. If we do this substitution, we're going to get x arc sine of w instead of x squared. And then the dx is going to turn into our 1 over 2x dw. And then you can cancel things. The x here and the x there cancel. We do a little bit of tidying, and we get 1/2 the integral of arc sine of w dw. Oops. And that to me is the perfect element for integration by parts. We pause. Certainly, first of all, we check to make sure that it's actually simpler than what we started with. And it is. We had products before. Now we just have arc sine. At this stage, there's literally no substitutions that we can make. So in terms of clarity, which method to use, by parts is literally the only thing we can use. And for that, in terms of the u and dv parts, the only way that makes any sense, going through the steps, whatever I pick as u, I'm going to differentiate. Whatever I pick as dv, I'm going to have to integrate. The only interesting function is the arc sine. If I put it in dv, I'm going to have to integrate it, but I don't know how to integrate it. That's why I'm having a hard time in the first place. So I can't put arc sine in the dv. I have to put it in the u part. And that leaves just the dw sign or element to go in with the dv part. Once you've made that call, we start turning the crank again. We've picked those. We differentiate, and then we integrate. Our du becomes the derivative of arc sine, which is this interesting 1 minus x squared. Oh wait, it's not x's this time, it's w's. So 1 over w squared all square rooted. And our v becomes a w. I do my little mnemonic thing for the integration by parts formula, u times v minus v du. Our integral then becomes 1/2 times uv, arcsine of w times w, minus the integral of, oh, sorry, I forgot a dw here, minus w times 1/1 minus w squared, all square rooted, dw, close the brackets. And wait for the brackets to appear. And that gives us the final expression from that stage of the integrals. If you take a quick look at what we have now, the arcsine's there, but there's no integration left to be done here, so this is fine. We're done this part. This part is where I would say we have a third stage. We've done substitution, that simplified it one way. Then we did integration by parts, and that simplified it into a new form. It doesn't look simpler, like arcsine, I guess, is simple, but it does look exactly like another substitution integral where we have 1 minus w squared, its derivative is w, things will cancel, and let's pick z as our new variable, 1 minus w squared. If we do a substitution with that, then it'll match what's in the solutions. Let me know if you want to do that last step, but I think that should already be in what we have typed up in the PDFs. The key thing is to recognize what to do at each stage. All right. I'm going to leave that there on the screen for a second or two, or a minute or two. If you have any other questions, I see there's a couple people still with us. I know it's early days yet for a Wednesday exam though, so not having questions at this stage is totally reasonable. Yes, I've got exactly the same time tomorrow, Monday, and Tuesday. So every day leading up to the exam, I'll have sessions again. Sure. I just saw Grace's question there. ArcCos 2015 exam, absolutely. I'm just going to try to bring that up. It actually is in the practice problems as well. I think it's either Unit 9 or Unit 10, actually. I can find that out. Just looking for another resource of it. No, almost certainly Unit 11. Oh, so the derivative. So, right, implicit derivatives. I think it's Unit 5 then. Right, flipping through some questions there. No, it's not there. 6. Oops, no, I don't want solutions. Odd. Sorry, you don't put the solutions there. So I could have sworn we had this as a, all right, let's go for the exam version because as you recognize, it is for sure there. And we'll start with that. All right, full page. Integral, sorry, you said section 6. So close. Section 6. Right, finding the derivative of cos. Okay, that was meant to be a warm-up question. I'm just going to go a little full screen there, full width. So we'll do part A, and then we'll jump into part B. And I'm just going to do a quick save of this for reference later on. All right, so let's dive down a little further here. I'm just going to make some new pages to give us some space to work. There we go. All righty. So we start off with part A. The derivative of cos of x is negative sine of x. All right. Part B. Starting with the relationship cos of arc cos of x. And that's an inverse relationship. I start with x, then I do the arc cos, then I do the cos. I'm going to get back to what I started with, which was just x. So what does that look like when we start differentiating it? So we're going to take a derivative of the entire left-hand side. And if we're going to do that, we have to take the derivative of the entire right-hand side at the same time to keep it equal. Then what we found with the derivative of cos, so here's a chain rule thing, take the derivative of the outside function, we get negative sine of, well, before it was x, now it's the different inside, but that's fine. We'll have arc cos of x times the derivative of the inside. Now the whole point is we don't know what that is yet. So clean that up a bit, cos of x. But that would be it. I'd take the derivative of the inside, and then I'd be finished the derivative of that entire left-hand side. The derivative of the right-hand side, fortunately, is just 1. And what that lets us do is solve for the derivative that we want to know. Hey, what's the derivative of arc cos equal to? Well, it's going to equal the derivative of arc cos of x is going to equal 1 over this part here, negative sine of arc cos of x. And that gives us one of the formulas, I think in the videos, described as true, but not necessarily that useful. I'm just going to do a quick tab back to the actual question itself, because I think there is a hint that gets you over this stage here. Oops. Got off my page there. The trig identity sine squared plus cos squared equals 1 may be useful. So we're going to take advantage of that next. And that's the key thing for getting rid of this expression here. If we have, let's call this, can't call it x, but let's call it y. So if I have sine squared of y plus cos squared of y, that equals 1. And the insight, not at all obvious, but something that we have covered. So this is more of a recollection than it is created out of whole cloth. We take, what this lets us do is trade sine functions for cosine functions. If I can isolate for sine, I'm going to get cosines back. I like cosines because cos of arc cos of x, way back when we started, cos of arc cos of x, I could simplify just back to x. So that's what we're going to try to do. We're going to isolate sine. So we're going to have sine squared of y, clean that up, is equal to 1 minus cos squared of y. And so sine of y, where it's going to be the square root of 1 minus cos squared of y. And there might be issues with plus or minus here. We'll table those for a second. But that's the magic tool for this, because now I can do, instead of, I have a negative sine y. Okay, if I want negative sine y, I can just take negative of that root. And we can take that down to here. Our derivative is going to equal 1 over negative sine, negative sine, so negative square root of 1 minus cos squared of arc cos of x. Arc cos of x. And that, I'll bring the negative to the top. Square root of 1 minus, well, the whole point of cos and arc cos of x, cos of arc cos of x can be replaced just by x. But it was that whole thing squared, so I'll have 1 over x, 1 minus x squared. All of that was in a square root sign. So we end up back with the classic formula, the one we ask you to memorize, for the derivative of arc cosine. Sorry, I'm just having slight glitches with the feed. I think I was seeing some comments, and now there's a random pop-up with half of a comment from a student. Wasn't quite sure what that was about. All right, lost that feed. I'm just going to go back here. Facebook pages take a surprising amount of time to load, at least for me right now. That might be because of the video feed going through. So just bear with me for a moment here. Okay, you're welcome, Grace. Hope that helped. All right. Any other questions from other folks at this point? Oh, there we go. Yeah, I just saw it. I just briefly saw your question. There we are. Question 9. Sorry, just to clarify, from the multiple choice. And Anshul, the idea of these office hours is these would be the office hours. So holding it online just to increase the number of students that might be able to attend. If there's something that's not material related that you wanted to ask about, we're behind on emails, but we will be catching up on those in the lead up to the exam itself. So if there's anything question and answer type that certainly belongs in these sessions, and if there's anything else, then just send us an email and we'll get back to you as soon as we can. Multiple choice. Okay. Thanks, Theo. Let me just bring that up. I just wanted to verify, didn't answer the wrong question. Go to full page. Section 9. All right. Okay. So for this question, it's one of these piecewise functions. So the function definition is different depending on whether you are to the left of 2 for x values or to the right of 2. And if we're looking for continuous, let me just see what we can say about that. I'm just going to copy this over b and 3 over b minus x. All right. So we have a function which is b when x is less than 2, and b over, sorry, 3 over b minus x. 6 when x is larger than or equal to 2. Okay. So the most natural thing to think about is this function. If we pick b, let's say b equals 1, just as a hypothetical, what that would mean is that we have a function that's flat, flat, flat at height 1 until we reach this transition point at x equals 2. And then, it does something after that, so we have to be a little bit careful about how that all works, but there's going to be some other function. And what we're interested in is how that transition happens. If it's going to be continuous, they have to join up to each other. Well, we have some lovely tools to look at continuity. For continuous, what we're going to see or need to see is that the limit as x goes to 2 from the left of our function equals the limit as x goes to 2 from the right of our function. So as we cruise in from this side and we cruise in from this side, do we end up at the same value? So let's just try that out. The wonderful thing about these limits is if we're coming from the left, that means x is definitely less than 2. So we just get b, and there's no x's in that. So that's, yeah, no matter where I come from along the left, I end up at height b. Done. The right-hand side is a little more interesting. If we're coming from the right, then we're using this branch, and we would be over 3 over b minus x. This time, when we're evaluating the limit, all we're doing is subbing in x equals 2. There's no problem with that. There's no dividing by 0, it doesn't look like. So b minus 2, that's what we get. And so as we're working on that, we can set those two, we need to have those two values equal to each other. So we are going to force them to be equal to each other and see what that means for our b values. So if we need to have b equal to 3 over b minus 2, another way to say that, bring the b minus 2 up, is that we're going to have b times b minus 2 equals 3. That's b squared minus 2b, and I'm going to foreshadow where we're going with this by moving things to the other side. And then we have a nice polynomial. We can see pretty quickly we can factor that. It looks like a b minus 3 and a b plus 1. Just going to go back to the question for 1 second. There we go. Those values look kind of familiar, aside from the slight typo in one of the questions, one of the answer options. So b equals 3 or b equals -1. So that, at first glance, seems like our answer. If we had those two values for b, then we're not going to have this break. We're going to have a smooth transition at our x equals 2 transition point. So with that in mind, though, let's just check our answer here. Let's put b equals -1 and write out our function. So f of x equals b, and then 3 minus -1 minus x, x less than 2, x greater than or equal to 2. Oops. Write that a little more tidily. And that actually seems, I think, okay. I'm just looking at this because one of the other issues we have to worry about with functions and continuity is dividing by 0. And if we do this and x is always bigger than 2, we're going to minus 3, minus 4, minus 5, minus 6. That actually seems all fine. However, there's a little gotcha here. For the b equals 3 answer, we get that function. And if you take a careful look at that function, when b gets closer and closer to 3, at x equals 3, we divide by 0. And that implies that it's not continuous. So this is a double-layered multiple choice question where you can kind of do the straightforward, naive, look at the formula for the function itself. Oh, look, there's a transition at a specific point. Let's make sure that works. But if you're thinking continuity, there's also the other things to keep in mind: dividing by 0, square roots of negative numbers. These are things you can't have in your function and still be continuous. And that turns out to be an issue here. So at the end of the day, b equals -1 is the only one that should work for this particular problem. And so the answer here, I believe in the solution, should be A. All right. Just checking in the comments. All right. So did that make sense, Theo? And okay, you're welcome. Mackin, all the solutions should be up. So I'm just doing a quick opening of the pages here on cue. Certainly there was no deliberate leaving out of the solutions. Are you part of the online or part of the main campus course? The exams are very similar, but they're different PDFs. So if there's an issue with the PDFs, it could be from that. Sorry, everything is, of course, taking its sweet time loading now. Main. Okay, let me just take a quick look there. One of the issues we found, for reasons that are totally unclear to me, is that sometimes the annotations that we put into the files are invisible to some PDF viewers. Yeah. So I can read off the solutions for you if you like. I'm happy to do that. My thought would be if you download the PDF and just try a different viewer, it might show the annotations. For the, just confirming I got the right exam, yeah, December 2017. Let me actually type these out into a reply on the comments, just so you don't have to worry about me misreading them. Art. Page. 1 second. Everything is loading. Oh, the answer keys are all posted on OnQ. So if you go to the Math 121 website, OnQ site, on the right-hand side, actually, I can just show you. Being a bit silly here. Yeah, let's do it this way. And in fact, this way you can actually see the solutions. Let's give, here we go. The internet's falling over a little bit here, but here we go. So both the online and the on campus have basically the same layout. There's a link over here for exam information. And if you click on that, it will take you to a page with the blank and exams with solutions. Let's pop open the 2017s. There we go. So all the solutions are listed there. So ACA, and with annotations explaining the rationale, DCB, and BDD. That should be the end of that. Yeah, that's 10. So those would be the solutions that I would be pointing people towards for using the exams for study purposes. Okay. Okay, so I think it's the issue of just not knowing the solutions were there. Sorry. Yeah, we tried to reference the exam information page as often as possible in class and online, just to say that's where we posted the list of things you need to memorize, all that stuff. So I apologize if it wasn't as visible as we would have hoped to everyone, but that's where I would go. No problem. And now you have 3 exams with solutions, so you're just looking for one. Alrighty. Any other questions on your lists? Or if you want, you can come back tomorrow after reviewing those solutions and seeing what makes sense, what doesn't make sense. That's what everybody was thinking this weekend, is hooray, more calc. Hi, Angela, I just saw your note. 2015, section 7B, absolutely. Let's go to that. I think we have that exam open. Section 7B. So this is blatantly taken from the practice problems. I'll tell you that right up front. Given my success record with finding those on the spot, actually, I'm almost sure this is in Unit 10. Let me just check here at the bottom. Yeah, so I'm going to full screen here. If you take a look at question 71, this is from Unit 10, it's basically the same question. So in that scenario, we didn't have a specified height, so we added some more details. But if you're looking for a compare and contrast example, that's definitely where I would look. All right, so with that all being said, so part A was finding the antiderivative. And if that was okay, I'll skip to the end of that one. Let's go here. So you had your V, which was mg over k, 1 minus e to the minus k over mt, I think. kt over m, I think how you write it. And so your h of t, which is the integral of your velocity, with one little gotcha. This was velocity, but it was downwards. So we need a negative sign in here to be the derivative of your height. If you're going to differentiate your height is decreasing. So dh dt, its derivative is negative. And the only way to make that happen is to slide a negative sign in front here. So if that's okay. And again, feel free to type a comment if there's something that's not clear. So we have our integral, and I won't go through the stages here. I'm just going to put it in here, and then we'll jump straight to the answer. dt, we should get negative mg over k times t, oops, forgot the exponential, t minus m over k e to the minus k over mt plus a c. And I would tidy that up a little bit. G over k, t plus m over k, e to the minus k over m t plus c. So that would be our solution for the height as a function of time. I'm just going to go take a step back. I don't think we had enough detail to figure out plus c yet. Oh, assume the body starts at h0. All right. So at t equals 0, h is equal to h naught. So we can sub that in to this expression and actually solve then for the value of c. So we'd have our height is h naught. That equals negative mg over k. T is 0, just looking here. And then we have m over k, e to the 0, and plus c. And the important thing to remember here is that e to the 0 isn't 0, it's actually 1. So if we start solving around for this, we get c is here. Let's bring everything else to the other side. It'll be h naught minus m squared m times g, and then 2 k's on the bottom would be k squared. So that would be our expression for the c, and we put it all together. We'd sub that back into there. I guess we're going to need that formula. So I'm just going to build that out for a second. For part B, our height is going to be equal to negative mg over k, t minus m over k, e to the minus k over mt, plus h naught minus m squared g over k squared, I think is what we ended up with at the very end of all that. That was our c. Again, feel free to type a comment if anything goes off the rails here. Then the follow-up was, what do we do with that? So a skydiver jumps out of the plane at a height of, okay, so there's our initial height, 2,500 meters. Bring that a little bit larger. And we have to, she's going to search for 15 seconds to find the handle of her parachute. A parachute should be open 1,000 meters above the ground for safe landing, and we have a bunch of constants. So basically what we're trying to do here is use the fact that we have h naught is 2,500. And what we want is the height at t equals 15 seconds. So we're essentially plugging in the values here. So yeah, you can find that value there by plugging in all the numbers. So there shouldn't be anything magical at this point. It should just be h of 15 is equal to negative, now I flip through and just find what our values are. M is 75, k is 4, so minus 75, g is 9.8 over 4. The time is 15, so I'll put it in blue. Minus 75 over 4, e to the minus 4 over 75 times 15, close bracket, plus h naught, 2,500, minus 75 squared times g, which is 9.8 again, all over k squared, which is 4 squared. We do all that calculation and you get a number. And at the end of the day, you just ask yourself, is that number above 1,000 or below 1,000? And the toughest part, honestly, is just making sure there's no computational mistake as you go through your calculator with all the brackets on that. Is there something specific in there you'd like to dive into more? Oh. That's interesting. We always like to have solutions match. Sorry, I just saw the other quick note about the exam information. If you go to the main page for main campus online, doesn't matter. I'm just going to bring this up for a second. There we go. on the bottom right hand, or sorry, on the right hand side at the bottom of the course resources list, there's the exam information page. And that'll take you to the page where the old exams and solutions are. All right. Let's just do a quick double check on the solutions then. Oh, I see one mistake for sure. This, sorry, let me go larger. Might be a shrunk screen. This looks incorrect. This should be 4 over 75, not 75 over 4. There's a bunch of m over k's, but some of them are k over m's, and we definitely got them swapped. This should be 4 over 75. Does that, so first off, my apologies. I should have caught that earlier. Second of all, does that explain the discrepancy for you? Yeah, my guess is the way I usually do these things to avoid calculational mistakes myself. I actually write it out longhand and then I type it into software because then I make fewer mistakes, or it's easier to correct a mistake rather than having to redo the whole calculation. In fact, that's what I'm tempted to do right now, but it's quite possible that the final answer is correct, even though the intermediate value is not correct. That it's just a typo of copying out the 75 over 4 versus 4 over 75. But when we did the calculation on the side, we did it correctly. Yeah, so there is a solution error, but it's not with the final answer. It's with one of the intermediate stages, and it's a typo rather than an actual process error. Test number 2, question 3. I don't think so, but I'm open to the debate about it. So let's take a quick look. If we go to the test information page, term tests, test 2, right? Test 2. Test 2 solutions. All right. We're loading. That's it. I think it's the last question. All right. Even just looking at this, so there does seem to be something dodgy because the base radius is 8, or sorry, the base radius is 5, and we're claiming that you need an 8 centimeter radius to get the best volume, which would be impossible. H equals 4 makes sense, but I think we might have messed up this part of the calculation. Now that you look at it. Okay. Yeah, just as a first glance, that is insane. That number is not physically possible. Okay, thank you for that. I've got 2 notes for things to go fix myself this afternoon. Clarify. As far as I remember, the height is correct. I think it was the calculation of the radius that is dodgy. 12 minus h. Oh, yeah, it's not 12 minus h. That's crazy. There's no way that's right. Yeah, I'm just looking at my diagram. The 12 minus h is the alternative height of the other part of the similar triangle, blah, blah. That's not the radius, though. So I think the 4 is probably correct, but not the resulting radius. My apologies for that. That makes 0 sense. 12H in 2015 7B. So excellent comparison work. That's good. Yeah, absolutely. If there's something wrong with the grading of it, then we will fix that. Absolutely. What I would recommend is that you use the the form online. So on the test information, sorry, we have it right here. So let's bring it back. Down towards the bottom, make this a bit bigger so you can see it. Marking rubric test regrading. So in this section here, there's a form that you can submit if you think something was odd. Usually the markers, once they see something going wrong in a whole pile of people's papers, they usually catch it, and maybe they just didn't tell us about it to fix the solutions. But if you believe that your answer was correct and it was marked as wrong, then please do use the online regrading form just to let us know what the issue was. 10/3. I feel like there should be a 12 involved. So 10/3 doesn't sound immediately correct. It's not, I'm not saying it isn't, but whatever your, if we just go back. Yeah, so it's up here. Sorry, I wish I could draw a little more large. Your radius is 5/12 of 12 minus h. So it'll be 5/12 of, it'll be 40/12, which I don't think is a nice number. 40/12. Oops, that's 740. 40/12. Oh, sorry, 10/3. Yes, I take it all back. The 12 and the simplified a bit. Yeah, so 10/3. Absolutely. Alrighty. Any other questions while we're here? This is good. We're getting things clarified. Sure, I just saw your question there, Pendle. Sorry, just a quick follow-up to Angela there. It doesn't affect it because we never used the radius. It was all about the h, and the h value was correct. So the radius was just a follow-up question about what do you get. Yeah, what was the follow-up question on the derived value r when h was what we spent all our time calculating? Sorry. So question 38, number 7. Question 38, number 7. Sorry, unit 7. Yeah. So it's unit 7. Right. Interesting. Okay. I think I'm looking at the wrong one. No, optimization, 38. Oh, the A's and B's there. Okay, sorry. I don't see any A's and B's in this question yet. All right. So if we go to here. I don't think we actually, the A's and B's weren't actually involved in the derivative for this question. We took a derivative early. Oh, sorry, those A's and B's. Sorry. I haven't looked at this particular solution in a while. All right. So the short answer is they're always treated as if they were a number, because they are. They're just a number we don't happen to know. So when you do the chain rule, let's do that here. So I'll just copy the formula over and take a quick look here. Pardon me for 1 sec. Sorry, I just lost your comment window. There we go. So our r of x is a squared plus x squared. Bring it back to here. R of x is the square root of a squared plus x squared plus the square root of L minus x all squared plus b squared. Yeah, perfect. All right. Then as we take the derivative, let's actually write this the way we should if we're going to differentiate it, which is writing it as a power, because that's easier to apply our rules for. So we're going to get 1/2 a squared plus x squared to the negative 1/2. And then we take the inside and we differentiate it. And then the key thing here is just to think, if a is a constant and it's not being multiplied by x, the derivative of a constant is 0. The temptation sometimes is to look at that a squared, but if you feel like that's leading you astray, if your intuition isn't working, do a little side calculation and just say, hey, what would the derivative of 3 squared plus x squared be? Well, that would just be the derivative of 9 plus x squared. Okay, I don't care if it's 3 squared or if it's 9. It doesn't matter how you write it. It's still a constant. So the derivative will still be 0 plus, oh, the x squared has something meaningful. It has a 2x. And so that's where we get that 2x from, in the solutions that are online. And exactly the same thing applies to the second term. You get your whole thing again, L minus x squared plus b squared. Just change the power first, the negative 1/2. And then we differentiate the inside. That plus b squared at the end is like plus 5 squared, doesn't matter. It's a number. The derivative of a single number with no x's multiplying it is going to be 0. And then you get your 2 L minus x. And if you're super careful, taking the derivative of the inside of that gives you a -1 multiplier because there's a negative in front of the x. And that would be the whole package of that derivative there. Does that make sense? Any follow-ups on that? Perfect. So yeah, it is, dealing with the letters is certainly more challenging than numbers, but that's only because our intuition based on earlier derivatives was built with numbers. I would never put it as part of a solution, but if you do a little side calculation just to mentally check yourself, put in a number, see what you would have done if it was a number. We tend to make fewer mistakes doing that, and then go back and say, oh, let's apply that same approach, that same format to the constants a and b instead of 3 or 5. Perfect. Okay. Any other questions still out there in anyone's mind? All right. Oh, okay, go ahead. Oh, I think you sent a photo through a different channel. I'm not sure how easy it is. Yeah, let's see how this works. I am far from a Facebook proficient person. Question 2. No, that was that one. Oh, the Madrid web work question. Yeah. So what was your question related to that? So we have the formula. I'll get that copied in here. So it's 12 hours of daylight, right? Yeah. It's 2.4 sine of 0.017 t minus 80. And you're trying to find the average value of h over different periods. Sorry, I'm just going to go back to the other feed, which is probably where your comment is. Okay, so the integration, fair enough. So the integral of h dt, actually, let's just do it on the same line rather than complicate our lives. There we go. So we're going to integrate this with respect to t, and that's going to equal the integral of all of this with respect to t. So let's do the super easy part. If we have 12 and we're integrating, we get 12t. Then it's probably worthwhile actually breaking this down to the integral of just the sine. And here, in fact, because the numbers look ugly, it may not be an advantage to keep it as numbers. In some ways, letters would be easier. But what I would be thinking here is either a substitution, if you feel that that's sort of how you work, though honestly, to me, a guess and check is probably the easiest. Because at the end of the day, this is like sine of t. There's no t squared, there's no square roots, it's just t in here with a bunch of numbers and a linear function of t. So I would be doing a guess and check thing. So I'd be saying, well, what if I have to integrate sine of 0.017 t minus 80? I know it's going to look something like cos of exactly the same thing. And here we get to practice the differentiation skills. So I think it's going to look something like that. So we're guessing and checking. So how do we guess and check? Well, we differentiate what we have and see how close we get. If we differentiate with respect to t. So we differentiate cos, we get negative sine of the same thing again. And then we also get a multiplication of 0.017. And that would be it. That would be the entire derivative of the inside. So going this way, the derivative of what we started with gives me negative sine of blah, blah, times 0.017. And if I look for the pieces that are extra that I don't want, it's the negative and that constant. And so all we do is we tweak our answer. So when I put a negative 9 and I divide by 0.017, everything is going to get, everything I don't want is going to go away, because we'd have that in the derivative. I'd have a negative 1 times that. Those cancel and those would cancel, and we would be good. So we just slide that into our guessing and checking answer. At least that's, I don't usually do it in that much detail, but that's the safest way, I think, to do a guess and check approach to this. If that doesn't feel comfortable, then another alternative, which is entirely reasonable, is to do the integral of sine of 0.017 t minus 80 dt and do a substitution. With a substitution, you would let w equal the inside function, 0.017 t minus 80. And when you do that, it's going to take care of the bookkeeping for you. We take the derivative of this. This is really simple. There's no sine or cos anymore. So you get just the 0.017 times the derivative of the inside there. That's just 1. Don't need to show that. So 1 over 0.17 dw gives us dt. And I want that because it's the same thing that's in our integral. So we'd get the integral of sine of w, nice and simple. And then instead of dt, we would have 1 over 0.017 dw. Like, oh, that's not bad. Then we tidy 1 over 0.017 sine of w dw. Like, oh, that one we know how to evaluate. The integral of sine is negative cos plus c. And then, oh, we have a w, so we go back to x's. Gives you the same answer, or sorry, back to t's, not x's. We have 0, we have a negative sign, so I'll bring that out. Erase that. Negative 1 over 0.017 cos of w is up here, 0.017 t minus 80 plus c. So there are two ways to get to that integral value. Okay, I just saw Angela's question. Any follow-ups on that though, Pendle, before we do that? Okay, yeah, especially, sorry, let me go back one stage. Anytime you see something linear, so it's not t squared or anything else, but complicated, then yeah, substitution is a nice, safe way to handle that. It's a very procedural way to do it. You're not sort of doing it all in your head, and it takes care of how the constants work out for you. So perfect, that makes sense, then go for that. All right. Okay, so I just saw two questions, one from Angela, one from Eva. I'll do Angela's first, and then we'll do Eva's. Let's go back here. Unit 623. All right. All right. Okay. All right. So, Angela, what was the major issue with this one for you? Was it dealing with those constants again, sort of the A's and B's? So I'm not seeing any new comments popping up there. In the solutions here, what we took advantage of a little bit was, I think, the previous question, well, two previous. We had a similar formula for number 20, and that led to a bit of a shortcut being taken on 23. So the two are related to each other that way. All right, I'll wait for some feedback from you, Angela, in the oh, there we go. Such solutions. Okay. So all of these questions fall into the same, sorry, not all these questions. Questions specifically like 21 and 22 and 23, number 20, all fall into the same pattern in the sense that you have a formula and it has some undefined parameters in it. Let me just make sure that's right. Perfect. And that's our function. And then you're given some information about not just locations of coordinates, but the fact that it's a local maximum or a point of inflection at some particular location. So the key thing is how to turn those into mathematical statements. So here you're told that you are given a, here we go, a local maximum at x equals -5. So a local max at x equals -5. As soon as you say it's a local maximum, then you know it also has to be a critical point. As soon as you say it's a critical point, then you know that f prime of x at that location, let's be more specific, at -5, the slope has to be 0 at that location there. The follow-up part, the point of inflection, follows the same logic. A point of inflection is where you transition concavities. Oops. Concavities. And as soon as that's the case, concavity second derivative, and sorry, I told you it was -3, I think? -3, -7. The second derivative of your function at that specific location has to be 0. And also at -7 too. And what those do is they give you equations that you can then solve for, or use to solve for a and b. So if you take the first part, we take the derivative of our function, being super careful with the constant handling. The derivative of any exponential is the same exponential. And then we take the derivative of the exponent. So we have 1 over b and negative. And then we're going to have 2 times x minus a. Okay. So that gives us, we're going to set that equal to 0. E to the minus x minus a all over b squared. And then minus 2 over b x minus a. And the wonderful thing about setting things equal to 0 is we can just find the roots. This is not going to be a root because that's never equal to 0. We can divide through by it. Exponentials also never equal 0, so we can divide through by that. And by the time we're done that line, we have x minus a. Actually, yeah. So x equals a. But wait a minute, we actually knew what the x value was. We had the critical point at x equals -5. So we only have a critical point at -5, so we get our a equals -5. What we noticed early on is that that didn't tell us anything about b, because b got canceled out pretty quickly, but it gave us one of the values. And so now we know our function in a little more detail. It's -x minus a, which is -5, so it's x plus 5 at the end of the day, all over b and that term squared. So what we would do is find f prime of x, and then find f double prime of x, combine it with these statements, set it equal to 0, and that's what we have in the solutions moving forward. The second derivative is uglier simply because there's a product rule that we need to use to get to the second derivative. But it's exactly the same process, and we can still cancel the exponentials. We set things equal to 0, and things tidy up fairly quickly after that. So that would be the process for solving that one. Does that give you enough of sort of a structure for the solving process? Sorry, I know there's about a 10-second delay between things at this end and the projection of the video, so there will be long, significant pauses there. Okay, so in terms of process, really this boils down to a demonstration that students understand the connection about, okay, a local maximum, that's fine. We know a lot of things about local maximums, but in terms of setting up actual equations, the single biggest thing that we can take advantage of is local maxes are critical points. Critical points are where the derivative is 0 or undefined, but 0 in this case, the most common case, and then being able to use that to build a mathematical equation. Otherwise, it's just kind of, okay, things are true, but I don't know how to solve for anything. You need to boil it down, take the words and translate it into math in a slightly different way than you do in related rates or optimization problems. All right, so Eva had the question about Unit 9, Question 6. So I'm just going to bring that up. 9, Question 6. Question 6. Oh, the bicyclist. Okay. Okay. Yeah, I guess this one is definitely an interpretation question. Can you say what was it that you struggled with most, or what in the solutions didn't make sense? So the Riemann sum usually I think of as heights and widths. Is that what you're thinking? Like a left-hand sum or a right-hand sum? Let me take a step back just so you don't have to type too much or as you're typing. As long as you connect the area under the curve, so as long as there's some idea of how much area is between this curve and the 0 line, and then how much area is between the 0 line and this area. Sorry, it keeps jumping around. As long as you capture that in some reasonable way, then we're happy. The approach that we use in the solutions, I believe, is essentially like going back to grade 4 and saying, hey, what does 1 square represent in terms of area? And the only issue is getting the units right. So we have t in hours and velocities in miles per hour, but each square is 10 miles per hour high, but only 1/6 of an hour wide. So we had to do that kind of unit transformation, basically getting the delta x right. So yeah, the trapezoid rule would actually probably give you a very good estimate. Left or right will be probably pretty awful because a lot of the values are 0. But yeah, if you took a left and right and averaged it, that would be totally fine. Just be careful about the values being, or the delta t's here being 1/6 as you go through the process. But absolutely, you'll see in a lot of the questions where some estimation is required that any reasonable estimate will be accepted. As long as you say, hey, I'm going to use the left and right hand rule or the trapezoidal rule, then use that, totally fine. Okay, just saw a new question from Pendle there. Eva, please feel free to type a follow-up if you like. Okay, more than welcome. 2017, number 8. Let's see what we have here. Sorry, I don't have the exam open yet, so we'll open that up. Okay, I'm going to open the CDS version, which is probably the same as the main, but for anyone who's main campus. All right, 8. Oh, the voltage, sorry, just to confirm the voltage question. Okay. So literally it would be the numeric value that you end up getting. So I'm just going to open up solutions in the interest of reminder for those who hadn't seen it. All of the solutions are posted online. So the key thing is to know how to find them. I'm not sure if this is weird. Oh, that's what happened. Weird. There we go. So if you go to the exam information page off of OnQ, all of the old exams and solutions are posted there. A few scrolls down. So let's just take a quick look at that. Right. So honestly, it was filling in the blanks. I don't think I can blow that up, so I'll open a different view. But that's where you can find it yourself if you like. There we go, full page. So if the derivative process made sense, what we used was v as a constant. So we were basically just differentiating 1 over r. That gave us negative 1 over r squared, and then the derivative of r with respect to t from the chain rule. And then we just went through the question and found the ingredients. The voltage is 10 volts, so we got 10 for that. The resistance is 7, so we used a 7 for that. And the dRdt was that the resistance was increasing at a rate of 2 ohms, so we used a 2 for that. And barring any typos, no, 20 over 49 is correct, negative. And it just so happened that the value ended up being it should be negative 0.41 amps per second. The negative tells you that it's decreasing, and it's 0.41, not 0.39. So it's decreasing at more than 0.4 amps per second. And now I'm just doubting myself further. So let's do a quick 20 divided by 49. Yeah, 0.408. So definitely more than that threshold of 0.4. Was there more to that question that I'm missing, or does that make sense? And Mackin, I saw your text. We'll do that one next, number 5. Yeah, fair enough. I'll ask the same question for you, Mackin. What seemed to be the obstacle working with the solution for number 5? Was it the computation, or I mean this question could be done both graphically by focusing in on the interval from 2 to 5 and just sort of looking at the graph. Looking at the graph on that interval, or it could be done by doing the sort of brute force integral, but remembering how you can calculate the integrals as areas under the graph. So triangles plus rectangles, there's strategies for that as well, which is what the numerical calculation there was. Okay, so the first key is, as long as you have one way, you're probably okay. So if you could just look at the graph and ballpark that it dropped quickly and then flattened and then went down slowly, the average is going to be a little bit above that middle ground, just because there's more above that than below it. But the actual calculation itself, let's bring back this. I got a graph going here. So there's a line like that, and a line like that, and a line more like that. So ballparks. And the key thing was you needed to know the integral of that function from 2 to 5. And the main observation is that's the area under the graph. And you can do this a bunch of different ways. The way we did it was to do it as rectangles and trapezoids. But if that doesn't occur to you, you could absolutely have done it as triangle, rectangle, triangle, rectangle. So some of these ingredients, I'm just going to go back to the picture. I think it was 3 and 6 and 2. So 6, 3, and height 2. Let's get rid of that. Some nice straight lines for this. So you could have said that this area was 3 by 1, but divided by 2 because it's a triangle. This area was 2 by 3, so that's 6. That area there is, I'm trying to draw it inside the things. It's a 2 by 1, so that's 2. And this one here is a 1 by 1 triangle. Not the scale the way I'm drawing it. Let me just double check. Yeah, it'd be a 1 by 1. We should have an area of a half. So your area is 3 halves plus 6 plus 2 plus a half. That's 8, 9, that's 10 overall. So that's another way to get to the area. But what it boils down to is an area calculation. However, you can break down the area in that picture using triangles, rectangles, and trapezoids is fine by us. It should all give the same answer at the end of the day. For Eva's question, the grading mostly was done. There's one TA who's still doing stuff yesterday. I actually haven't had a chance to check today, but if they're done as of this morning or this afternoon now, we'll send it out to you as soon as we can just collate the grades and get them into OnQ. So hopefully later on today, latest tomorrow, I would expect. For the online people, we're behind. I'm doing that marking this weekend, so we'll get test 1's almost done. We'll get that to you, and then hopefully it'll be a big production on Sunday. We should be able to get you test 2 back, hopefully Sunday or Monday, and test 3 before the exam. Oh, going back to Pendle's question, the question actually isn't the integral. The question is the average value. So if you look in the answers here, so let's highlight, not very helpful. The integral is only one part of it. So going back to here, that's the integral, but the average value, the average height, first of all, 10 can't be the average height because the average height's something on this scale. If it helps, what I find makes it concrete is to think of this as temperature. Oh, it was 6 degrees when I got up. Around the middle of the day, it was 3 degrees, and then it was 2 degrees by the end of the day. Well, the average temperature is going to be somewhere between 2 and 6. So that's the only acceptable answer if we're talking about averages. In terms of calculation, what we're doing is we're taking this 10 area and we're squishing it down into something between 2 and 5, but that's a rectangle. So the area is 10, and we want to know the height. Well, if it's 3 by something, it turns out to be 3 by 3.333. That'll give us an area of 10. If you look at the solutions, what we have is the more explicit formula, 1 over b minus a, which is your width, which is here, or sorry, 1 over width, times the integral from a to b of your function. And so for us, that gives us 1/3 of that 10, so we get 3.333. Whichever way you want to think about it, that gives you that same final answer. The average height The average temperature, if you think of this as temperature, is just a little bit above 3. If I drew a horizontal line there, I'd find the same area above and below on that curve. Doesn't look particularly good on my sketch because I wasn't able to draw it to scale, but it looks better on the solution, whereas more precisely generated. So I'm just going to take a quick look at something. It won't affect us directly, but I think we can do that here. Okay. Sorry, just thinking for future classes. Any question? All right. All right. Any last questions for today, knowing that there are sessions tomorrow, Monday, and Tuesday, and that they will hopefully go more smoothly technically than this one did? Okay, then I think we'll call that a day, and I will see anyone who has new questions by tomorrow or Monday or Tuesday at the same 12 o'clock start time till 2 p.m.-ish whenever we get finished the questions for that day. Thank you very much for being here, and we will see you maybe at a later session or at the exam. Thanks.